Dear students, I welcome all of you in the another session of Traffic Engineering and Management. So we have been discussing about the module number 3, that is Lighthill and Withamson's theory or Witham's theory. See, this chapter contains total 6 to 7 theories, out of which the most important theories are 3 to 4, such as the general assumption part, the main theory, and the signalized intersection theory. There are two other theories such as bottleneck theory, which considers three cases, and the another theory, that is queuing theory. That theory you have to done on your own because that is having the same criteria such as the main theory, just only certain elements are to be changed. So that is how we are going to conduct that. So I welcome all of you once again in the session of this traffic engineering and management, where we are discussing about the module number 3, and this particular module is Lytle and Rhythms theory. So what we are going to cover in this particular session is we are going to cover the main theory and the approach to signalized intersection along with the particular general part and the assumption part that we have covered in the last session also, but in this session we are going to cover that thing in very of the detail. See, just read this sentence. What has been written that by drawing analogy between the flow of fluids and flow of traffic, the traffic flow can be easily understood. Lighthill and Witham have contributed to this topic by their theory, which is based on the kinematic waves. Now, what we have gone through is that here he and Lighthill and Witham have tried to draw the analogy comparison between the flow of traffic and flow of fluid. Now we know that flow of fluid is some different kind of thing that can never be compared with the flow of traffic. But they have assumed that with the help of the concept of flow of fluid, we can understand the concept of flow of traffic also. And they have considered the kinematic waves theory. Kinematic waves which are being covered for the flow of fluids. They have considered that particular thing for the demarcation and establishment of this particular flow of traffic. Now, as I have already mentioned that this flow of fluids and flow of traffic can never be compared. See, why it cannot be compared? Because it is having certain limitation. What is the limitation? That it is based on continuous flow approach. Now fluid is something that flows continuously until it becomes empty. So this theory, flow of traffic, which is based on the fluid, is directly based on continuous flow. Now this continuous flow is being observed in the fluid dynamics, and this particular thing represents the limiting behavior of the stochastic process of the large population, which in this particular case is the total number of vehicles. So what I am trying to convey is that traffic can never be continuous unless larger stretch and long crowded roads are considered. So basically the limitation of this theory is that this theory is only applicable where the large scale problem is being studied, and where the principal part is the distribution of the traffic on the long crowded roads. So this is what we have learned, that they have covered, they have tried to compare the flow of fluids, then kinematic waves and continuous flow. And this can only happen when the large scale problem is being studied. So this is how you can understand this particular thing. See, there are assumptions that they have made. What are those assumptions? The equation of continuity is valid. They have thought that continuity equation is valid. That means, just like the law of conservation of energies, they have thought that there is a law of conservation of vehicle also holds good for the particular theory. That means inflow equals to outflow, plus or minus storage. This is what they have considered. And the second assumption that they have made is that at any point on the road, the flow they have denoted by Q. See, traffic flow is denoted by Q. The flow is the function of concentration K, means density K. This is what they have assumed. These are the assumptions. Let us start with the theory. See, consider a road length, consider a length of road ABC. A to B is the road length they have considered. This is single lane and one stationary observer is here at point midpoint O. So you can see. Okay. Now when this particular observer starts counting the number of vehicles passing from him, means in this direction or in this direction, he is standing over here. He is stationary because his position is fixed. Now when this observer will start counting the number of vehicles that is passing from this point, there are n number of vehicles in the length OB. See, n number of vehicles in length OB. The count will stop at the expiry of time t when all the n vehicles have passed the observer. Means when all the n vehicles have passed the observer at the time t, the count will be stopped. Now, at the same time, when the stationary observer is counting, a moving observer means whose place is being changed. A moving observer also starts at point 0 and he travels with the stream at u speed. See, this is u is the speed and t is the time. Now this particular speed u is less than vs. Vs means space mean speed. We have learned that. See, the time taken by this vehicle to cross this point to this point is called as space mean speed. We have learned in the very beginning of this chapter and third chapter also. So this ut is always lesser than vs. That is the space mean speed of the stream. And he counts the vehicle passing in. So what we have learned in this slide, we have learned that we have to consider the road length AB, that is the single road length. We have the stationary observer O, he is standing at the midpoint. Now as he is stationary, his place will not be changed. He will count the particular number of vehicle in the length OB. Number of vehicle will be n, and when this n vehicles will be over, he will stop counting. At the same time, when he is counting over here, a moving observer also starts counting the vehicle in this direction. The vehicle are traveling at the speed of u, which is less than the space mean speed that we have learned. Now see, the count stops at the expiry of time t when the n of the vehicle have passed over, that we have learned. Now, just pay attention. The moving observer has traveled a distance OC. He has traveled the distance of this OC. Moving observer, not stationary. So, number of length counted by the moving observer will be length minus length in OC. Total number length minus length in OC. Now see, total time is T, flow is Q, minus. He has considered the speed of U, taken time of T, number of vehicles is N and divided by small length of L. So, this is what the equation of this particular this moving observer. Now see, this N by L is called as K. And this K stands for density or concentration. So it will be Qt minus UK. Qt minus UK, and T is also here, Ku and T. It will be T over here. So this is the equation C. Now the flow which is related to the moving observer will be Q minus K into U, where the Q stands for flow, T stands for count time, K stands for concentration, N stands for number of vehicles that pass the O in the time T that I already discussed. See, now let us take another case. Suppose two moving observers are traveling at the u speed at the time t. So two moving observers are there. Speed is u and time is t. Now suppose the flow and concentration changes with time, and these changes are very small. But the observers have been told to adjust the speed u so that the vehicle those vehicles that which pass minus the vehicle which they pass on the average is same for that. So q minus ku is will be same for each parameter. So for observer 1 and 2, as the change is very small, it will be q1 minus k1 u1 q2 minus q2 u2. If we consider u, if you want to calculate u, then u will be here. See, this will be only u. So this will be q1 minus q2 by k1 minus k2. So this is called as delta q because this is the change. This is called as delta k because this is the change. So this is what U stands for. Delta Q means change in flow, delta K means change in concentration, and the equation will be U is equal to delta Q minus by delta K. See, but the number between the observer must remain the same, and the number of the vehicle passing at any point between the time which the observers pass is Q into T. That we have learned in the beginning, first slide. So we know that T is fixed. The flow will remain unchanged along the whole path of the observer traveling at the speed of u. Means what I am trying to say is when the change in flow is occurring, the waves which carry such change through the stream of travel is given by this equation. This is the explanation of this equation. U is equal to q1 minus q2 by k1 minus k2. So it will be delta q by delta k. This velocity relative to the road may be positive also or negative also, but it can never exceed this Ps, that is space mean speed. Now, if we consider that Q and K are functionally related, then this can be denoted with the help of this equation. Phi equals to dq by dk. So, on the fundamental diagram of traffic flow, this dq by dk is the slope of the tangent to the curve. So you can see dq by dk, that is phi. That is this particular slope of the tangent. See, this is the slope. But you know that q is equal to k v bar s. So we have to disintegrate this. So dq by dk, this will be the disintegration of this equation. This equation's disintegration will be this. And if we put dq by dk is equal to phi that we have learned, this equation will look like this. So we can see that the speed at the crest, see this, will be 0. Speed of the wave propagation, see this will be 0. Now another scenario is that consider the road stretch where the traffic is dense in front of A and less than dense behind the B. So this is A, this is B, and whose fundamental diagram looks like this. So the slope of the curve is steeper at B than A. You can see this is steeper slope at B, this is B, and this is A. So you can see with compared to this is very steeper, very heavy edge is there. So a shock wave will now be generated if the flow changes from A to B. If A to B the flow is being changed, the shock wave will be generated. And the speed of the shock wave will be delta Q by delta K. That will be QA minus QB by KA by minus KB. So flow divided by concentration QA minus QB and KA minus KB. So that will be delta Q by delta K. In the experiment of two observers, the speed of shock wave will be U and the speed at which the two observers travel. So see friends, this was the theory of particular lithiums and light hill and lithiums theory, main theory. Now there is another important theory, that is this approach to the signalized intersection. See, the approach to the signalized intersection. Now we want to know that what is the meaning of signalized intersection, that we have learned in the part of traffic signals and signs. See, the approach to the signalized intersection is an example of the shock wave where the vehicles are brought successively to the halt, means the vehicle are brought to the halt from flow QA to the concentration QB. So in the region of the halt vehicles, the flow is zero because the vehicles are at halt, they are stopped. And the concentration is the highest because the density will be highest because the vehicles are stopped. And that will almost reach to the jamming value. This region of halted flow and high concentration is propagated backward by means of shock wave whose speed is given by the slope of line AB in the figure. See, this slope of line, this particular line gives us the value of the speed when the region of the halted flow and high concentration speed is propagated backward by means of the shock wave. So this was all about the important things related with the light hill and rhythms theory. Now you have to go through the theory of bottleneck, that is very short theory, and the queuing theory that relates with the main theory. So here it is the completion of almost completion of your syllabus. I hope you have gone through the concepts thoroughly. Thank you so much.